Hi, today we've invited Dr. Daniel Berard here to talk to us about his career path from studying physics at McGill, his early research years, transitioning to his postdoctoral fellowship here at UBC in single molecule biophysics, and now where he is in industry.
Well, hello and welcome, Dan. How would you recommend getting into research early, like you did?
Yeah, if you're interested, if research is something that you enjoy and that's something you want to do, especially if you're interested in doing grad school, then yeah, try and get into research as early as you can. Yeah, then you start building up those skills, and you know what to expect. You'll get a good idea of whether you like it or not. Yeah, and I think it's a good idea to maybe try a few different research projects. Because yeah, every group, every project is going to be quite different.
Yeah, so you talked a little bit, you said you had this vision of going into industry pretty early on. What would you say are like the pros and cons for someone maybe not sure between academia and industry?
I guess it just depends what your goals are. If you're really interested in research, then probably academia makes more sense. Or if you like teaching a lot, then for sure. Yeah, I don't know, if you want to work on something that's maybe a little bit more close to application, then industry makes sense. So yeah, so I'm working on machines now that make lipid nanoparticle vaccines, so vaccines that will go into patients. And there's a lot of really interesting upcoming research in these fields too. So, and now I'm working on the equipment that will actually produce these products that, yeah, will hopefully help change medicine or help advance medicine. Yeah, and so that's very inspiring to me, and it's a change from what I was doing before. I guess another thing with academia is you kind of need to be pretty comfortable with failure, because when you're doing these new experiments, you're trying to solve problems that have never been solved, and doing experiments that have never been done, you're gonna run into problems that you didn't expect, and yeah, a lot of stuff is just not gonna work. And you're going to be redesigning experiments and redesigning them again and again, and equipment. And you have to be comfortable with stuff not working. I think that's part of the fun. When it does work, it feels great, and that's how you really, really learn something. Whereas now, in the position I'm in now in industry, it doesn't really quite have that same aspect to it, or that same challenge. It's like I'm working on this product design, it's a new product. That'll probably be released in a couple years or so, and I think we pretty much know that it's going to sell. We know that there's a market for it. We know that there's demand for it. It's pretty close to the application. Cytiva is a big company with a good reputation and a lot of similar products on the market already. So it doesn't quite have that same sort of, I guess, mystery to it. I don't know. Yeah.
There's an end goal that has been proven.
That's clear.
Yeah.
And we know, yeah, we're going to achieve that goal.
Okay, that's cool. And how would you say it compares in terms of like creative freedoms in terms of your projects or what you work on?
I feel like I have a lot of creative freedom either way. Yeah, maybe a little bit more so in academia. But even then, it depends on the project, and it changes with the project too. Sometimes when you've been working on a project for a while, your path of where that project is going to go gets a little more and more clear. Yeah, like one thing we were working on in the lab was at first it was a lot of like technology development, developing instrumentation to do new kinds of microscopy experiments where we would actually like trap single molecules in micro or nanoscale glass chambers. And you can look up Sabrina Leslie's research. That's the lab I worked in. It's really, really cool stuff. And as we were developing that more, we started doing partnerships with companies, and then the goals started to get more clear. And it's like, okay, here's our objective. Yeah, and now it's like we have to figure out how we're going to accomplish that. Yeah, and design all the experiments and then just start executing and getting results.
No, that's great. And then in terms of like maybe work-life balance or like the culture of industry versus academia, is there a big difference there you've experienced?
It's a good question. I think it just really depends on the company or the group itself. Even like now in the company I'm an engineer, so I work in the engineering team. So we kind of have our own office that's across the parking lot or we sort of like 3 sections. So there's a little bit of separation from the company. The company is maybe in the 200 to 300 people range, or at least what was Precision Nanosystems. So it's like, yeah, an order of magnitude larger than an academic lab. So there's many subgroups.
And you say you're doing stuff for like preclinical or clinical?
So the instrumentation that I'm working on is potentially for both. So yeah, I mean, we have a few products on the market that have been on the market for quite a long time, many years. We have systems for both, and we recently. So when I joined the company, or about a year after, or yeah, within the first year that I joined the company, we released a product for formulating just large quantities of vaccines. It's called the NanoAssembler Commercial Formulation System. And it's just like a fridge-sized lipid nanoparticle formulator. So what it does, you give it a big bag full of lipids dissolved in ethanol, and then another big bag full of mRNA or whatever the drug is that you want to encapsulate in the lipid particle. And you hook these up to the machine. The machine has a single-use fluid kit. So every tube or every part of the machine that the fluid touches is single use. So it's this one, you get this big kind of package, and it's all pre-assembled in a clean room, and it's been gamma sterilized. So it's sterile, you take it out of the package, you install it on the machine. The machine has pinch valves that pinch the tubing. The pumps are actually part of the pumps, like the heads of the pumps are part of the fluid kit itself, and they're magnetically coupled to pumps in the system, which is really neat. Yeah, and it's got this mixer on it, and so you install this in the machine. It's got all these valves and flow meters and stuff. And it will mix the lipids with the RNA, and you can program in like exactly what you want that recipe to be like. And it will mix them through this kind of like microfluidic type mixer. I guess it's not really microfluidic. It's like millimeter scale dimensions. So that's what's cool about this kind of mixing technology, is that you can scale the mixer size up, so it can be a microfluidic chip, or it can be quite large, and it still mixes via the same mechanism. And so it's a very scalable technology. So the smallest instrument that we have is called the Spark, and it's this tiny little thing that makes like tens of microliters of formulation, and it uses the same kind of mixer, it's just smaller. So the big machine is, like I said, the size of a fridge. It will make hundreds of liters of formulation, so it can make vaccines. Because everything's sterile and everything, yeah, you can make vaccines on this thing that will go into people. Yeah, so you can make like COVID vaccines on this. That's the same kind of technology that it's using. Yeah, and the single-use thing might not sound so great. You use this, you put this kind of large, complicated assembly of tubing on the machine. You use it once to make your batch, and then you throw it away. If you want to make another batch, you install another one. But that batch is hundreds of liters, so that, the waste of fluid kit is really nothing. And actually, it's better than the alternative, usually in most cases, which is, say you had a fixed stainless steel tubing assembly, which is also a very common way to do this. You have to clean it after your batch is done, and it has to be re-sterilized, and that's pretty complicated and actually uses a lot of chemicals, like sodium hydroxide. So you're really generating a lot of waste in a different way. And it's also very expensive because you need to validate it every time. So you need to run a long cleaning and sterilization procedure and then validate that it's actually clean and sterile. Whereas with the single-use flow kit, you don't have that problem. That's already been done before you even install it.
How long does it take to go from like a conception of something like as big a scale as that to actually rolling it out for people to use?
It's a lot of work. I only joined the company when it was almost finished, so I contributed sort of a smaller part to that. So I unfortunately didn't get to see the whole process of that being developed, but I have heard a lot about it. Yeah, it's a lot of validation, a lot of testing. Yeah, just it changes as the process goes on. What pumping mechanism you might use is going to change. Maybe over time, if maybe you have this first idea and you test it out, and maybe it doesn't quite work the way you expect, so you change it up. There's always design iteration like that. Yeah, but now I'm working on a new project, so I'm starting on this kind of thing up from the ground up. Yeah, so it's like starting with sort of just early prototyping of like pumping mechanisms, making sure that it's going to make good quality nanoparticles, and really focusing on user experience early on, I think is a pretty big part of it. And also just nailing down what our customers' requirements are. So what do customers actually need? And then making sure we can actually address that. Yeah, it's a high priority.
Okay, that's cool. Yeah. So it won't be for a while that you have it.
Yeah, this one's recently begun.
Okay, and then I guess a little bit of a change, but how would you say the process is different for someone maybe wanting to go into something like industry with biotech from a bachelor's versus master's, PhD, postdoc? Like, how does that change?
Yeah, I mean, I guess it would have been different going straight in from bachelor's for sure. Like I'm coming in with a lot of research experience, a lot of engineering skills that I've developed doing research, but I don't have that direct training as an engineer. So I guess I come in with sort of a somewhat unique skill set. And part of that is, I guess, being able to work with both engineers and scientists. So kind of helping to bridge that gap, I think, has been useful. Yeah, I guess it's just the more experience you have, the sort of higher level you're gonna start at when you start in industry. Yeah.
Is it fairly competitive though, or?
I think it's pretty competitive, yes.
Okay.
I mean, academia is competitive too. It's tough.
It's unavoidable.
Sure. Yeah.
So what would you say benefited you most then, like in terms of like coursework, or you said a lot of engineering stuff you learned on the job?
Yeah.
Like
it's all been pretty helpful. Like the coursework gives you the theoretical background, and you sometimes you never really know when that stuff's going to come in handy, especially in academic research. Yeah, even like having a good understanding of quantum mechanics helps you understand how fluorescent dyes work. And a problem, when we were doing all these fluorescence experiments in the Leslie lab is you have to deal with something called photo bleaching, which means that when you're using a fluorescently labeled molecule and you want to look at it on a microscope, you have to illuminate it with some light source, like a laser, that it absorbs. So it absorbs that light, and then it emits light of a different color, and you block out the laser light, so you just see the molecule itself glowing. And so the molecules kind of become their own light sources. But the problem is the more light you shoot at them, they eventually go dark. there's always some probability that it's gonna photo bleach where it just stops emitting light. It just the dye gets destroyed by the laser basically. Um, yeah, and there's things you can do to slow this process down, um, and it all works by pretty much by quantum mechanisms. Which, yeah, if you have some understanding of that, it sort of helps you, uh, yeah, figure out how to implement these things, I guess.
So you'd say physics
Yeah.
is a pretty good
I
background.
think physics is a pretty flexible background to have because it gives you a base from which you can learn, like build a lot of new, at least technical or science skills off of. It gives you, yeah, I mean, it's a good base from which to learn other scientific disciplines. Physicists and engineers, I think, take a lot of the same courses. Um, so, if you've studied physics, you have a lot of that already, and learning the engineering skills is, it's not like you're learning a whole new degree. Yeah,
Just a little
a
tack on at the
little
end.
bit. Well, yeah, there's a lot. Yeah, and it's stuff that I've just kind of learned along the way based on, yeah, just different challenges, just different problems I've had to solve in the lab.
If there's anything like you could do differently or any advice you'd have for yourself starting out, is there anything you'd say to young Dan?
Uh, Good question. Um, yeah, I mean, I'd maybe I would have gotten into research, or at least tried to get into research earlier, because I didn't in my first year of university. I think I maybe would have even tried earlier than that. I knew when I was towards the end of high school was when I figured out that I really loved science, and that's what I wanted to do. Uh, so I think getting into research or getting into an internship or something like that early uh, would have been ideal. I didn't until it was close, I think after my second or third year of undergrad was when I joined the lab. But yeah, doing something earlier. I think the earlier you start, the faster you start building up those practical skills. And it's definitely harder to get into those positions with less experience so earlier on. So um, yeah, yeah. But you can always volunteer in a lab. Yeah, the Leslie Lab has taken volunteers before. A lot of labs do that. So that's one way you can get started, at least get some experience. You can volunteer for a summer. Of course, if you can get the funding, that's better. You can apply for these NSERC awards, and sometimes there are other ones that are more specialized. And if you can get that, that's fantastic because that also means the professor doesn't have to pay you because they have funding. Yeah. So yeah, I mean, I think getting into research or an internship early is a really good idea.
No, that's great. Yeah, how about in grad school? Grad school advice.
Ooh.
Any misconceptions you had going in, like something you thought would happen that didn't, or vice versa?
Um, I don't know. I think because I was already working in this lab, I had a really good idea of what to expect going in. It was like I was just kind of continuing work that I was already doing. Um, yeah, so not too much for me.
Fair.
But yeah, I think it's good to make sure that you have a pretty clear plan or a clear goal for what you want to accomplish in your research. That's something to figure out with your supervisor. Uh, yeah, just have some clear objective maybe for the end. For me, it was I actually ended up doing a few different projects, which was also really cool. So I didn't really have that sort of clear objective going into it, but each project had its goal. Uh, the final goal was usually something quite far, like many, many years. That would be many, many years down the road. Uh, so there was not necessarily a plan to achieve that. It's more like the plan is to just get that path going to this goal. But sometimes projects change. So I went through I sort of had like, I guess sort of three-ish different projects throughout my PhD, which was neat to just, yeah, work on these different applications of the research you're doing. So, yeah, I think just make sure you have some kind of relatively clear plan. Mine was, I guess, mostly focused on developing instruments. So developing these CLiC instruments. So CLiC is this technology that Spring Leslie invented called convex lens induced confinement, and that's a technique for trapping molecules in nanoscale geometries on a microscope. So say you have two microscope cover slips that are very, very close together. You put your fluorescently labeled DNA or something in between them, and you press them together. Glass is really, really smooth, like almost atomically smooth. So around, you'll have this kind of donut region around this point of contact where the gap is like 10 nanometers, 100 nanometers, something in that range. And so any molecules in there are always going to be in focus on your microscope. They're only going to be able to move sideways, not up and down, because they're confined physically. So you can track them for a long time. You can observe them for a long time. And we were going further than that and actually trapping them horizontally as well. So making these micro or nanoscale wells, or sometimes grooves in the glass cover slip, like in the bottom of the cover slip, so that when you press these things together, you can completely trap molecules in these micro or nanoscale chambers. And now you can just observe them as long as you want until they photo bleach, of course. Yeah, which was always the limitation. But yeah, so that was pretty cool. So I worked on, I think I ended up designing like 5 of these, maybe even 6 of these instruments to do this like squishing, which was really cool. It's just they got better every time, sort of. Yeah.
No, that's great. And when you moved to UBC from McGill, did that change anything for your like the lab environment or like the projects you were working on, or was it pretty much smooth sailing?
I mean, I wouldn't call it smooth sailing. Like, we had to disassemble all of our optical tables. So we had at McGill, we had 2 like big optical tables, and each one of them had 2 microscopes on it, and they all had custom optics setups. So we had lasers. So it'd be 3 lasers for each table, red, green, and blue, that we'd use for just exciting different color of fluorescent dyes, different fluorescent labeled molecules. And we just had like tons of mirrors and lenses and other optical components that we set up to direct these lasers into the like combine the 3 lasers into a single beam, and then align them into the microscope, get them to be the right diameter, focus them to the correct spot. And yeah, there was some other equipment for like switching beams on and off really fast. Yeah, we had to take all that stuff apart and then rebuild it once we got to UBC.
Well, say you love engineering. Sounds pretty like you're doing a lot of that now. Do you see
Yes.
yourself staying in biotech for the next, 5-10 years, or maybe evolving into something different?
That's a good question. I could definitely see myself staying in biotech. It's really interesting, and there's a lot. Yeah, there's just so much to it. It's so multidisciplinary, and just getting more and more so, I think. So I would definitely, yeah, I could definitely see myself staying there. I could also see myself switching gears a little bit and doing something a little different, possibly. I think that's a big part of it. For me, the science is really what motivates me. The engineering part of it is, I guess, what just part of it that I find really fun. Yeah, just, but yeah, I find the science is really the motivation for me. So I'm just a very curious person. I like to learn new things. Um, yeah, so
The discovery and then
I'm always going to be in science.
Yeah.
I'll tell you that.
We won't see you off teaching only.
No, probably not.
That's fair. And where do you see like biotech going in the next, 5 to 10 years?
I think personalized medicine is becoming more and more a thing. Yeah. So, there's a lot of research being done into like personalized cancer vaccines, which is pretty interesting. Um, yeah, I mean, this lipid nanoparticle stuff seems to be taking off pretty well. We saw with the COVID vaccines how well that technology can work, and I think it gives you this way to develop new vaccines very quickly without having to do too much reevaluation of the safety profile, I guess. I mean, I'm not an expert on this stuff, but it's kind of my impression. Yeah, because if you're just changing the sequence of the RNA, the delivery vehicle is still a lipid nanoparticle. You're not using, an inactivated virus or something that maybe would trigger the immune response more, perhaps. Yeah, it's a very flexible technology.
What would you say, like, you do engineering, but like, what does your day look like? Do you spend, or a week? Is it very regular, or you get to tackle new things every day?
There are a lot of new challenges that come up for sure. It's like sometimes it's more regular, sometimes there's more going on, or more new things coming up. So there's definitely a lot of opportunities to learn new things. I feel like I have a good amount of independence at the company, and I can, have sort of some freedom to direct what I want to work on. Actually, what I did on the previous machine that we released, I spent some time working on something I did not expect to learn, which is explosion protection, because the machine pumps, large quantities of 100% ethanol, which is flammable, and if it's evaporating into the air, it can form an explosive mixture. And when you're dealing with like hundreds of liters, this can be like a huge safety concern. So the whole machine needs to be basically explosion proof. And yeah, I had to learn how all this works. Like, yeah, like purging enclosures with air to make sure that explosive vapors can't get in and then be ignited by electronics potentially. So that kind of thing is pretty new to me.
That's really
Yeah.
cool. Just always developing and learning on the
Yeah.
job. So, 5, 10 years from now, you'll know so much more.
Right, hopefully. I think that's important to me. I have to always be learning something new. Otherwise I get bored. There needs to be something for me to learn or like something challenging me. If I'm not, really learning new skills, then I tend to not stay as interested. So and here I feel like I have these opportunities to learn, which is great. And I did at the Leslie Lab too, which was fantastic. So yeah, as long as I have that, yeah, then I'm happy.
No, that's good.
Yeah.
I feel like one of the misconceptions I heard about industry is just like you go in and it's very formulaic, like very structured and the same every day, but it doesn't sound like that's true.
Not for me. I think it depends. I mean, I'm sure that it can be. I think it really just depends where you're working, what kind of career you're in. I think it definitely can be that way a lot of the time. Yeah, I mean, this company really, like Precision Nanosystems, was a UBC spin out. So, um, yeah, I mean, it really kind of builds on an academic background, like a lot of academic research, really. And I think a lot of that sort of spirit is still there, and the company still does a lot of research. So it wasn't really a huge transition for me in that sense. Like I'm still doing kind of similar work. I feel like the way that I work is pretty much the same. Yeah.
That's cool. Is there anything else you would want our audience to know about you and your career?
I don't know. I think that's good.
Okay.
Do you have any more questions? Or? Anything else you're interested in?
Do our co-directors have questions? What would uncertain people want to know?
I think maybe more for like the high school
Yeah.
audience. Like you said that you knew that you wanted to do research from high school, but what was that? How did you come to that conclusion at such a young age?
Right. Yeah. It was in grade 10 was when I had my first chemistry class and physics class, and I just had really good teachers that just were really good at explaining it, and they were fun, and just I don't know, I just thought the classes were really fun, and I found that I was good at it, um, and just very engaged in it, and I knew pretty quickly that's what I wanted to do. More of a clear direction that came more slowly over time. I didn't know that I wanted to do research, but I was definitely interested in physics and chemistry. I actually started university in chemistry. This may be another useful piece of advice is if you don't know exactly what you want to do when you're starting university, that's okay. Probably most people don't. Yeah, I certainly didn't. I had a rough idea that I wanted to do something like a hard science kind of thing or engineering. So it was pretty much between physics, chemistry, mechanical engineering, or electrical engineering. I chose chemistry because that's what I was best at. And I did that for a semester and then found I was kind of being pulled more towards physics. So I switched majors to physics. I actually did a semester, it was kind of like half chemistry, half physics. And just to kind of try out some of the physics classes. Yeah, and then decided I wanted to switch to physics, so I did that. So I ended up doing one extra semester in my degree, which like I could have squeezed it all in without having to do that, but I think then it would have been a bit of a tough course load. So yeah, it like if you're not sure exactly what you want to do, it's not hard to switch majors. And yeah, if you want to reduce the course load, you can always take an extra semester and maybe take like 4 courses a semester instead of 5, and that can be really helpful. Yeah, for maintaining a life.
Yeah, don't burn out.
Exactly. Yeah. If you burn out, then you're just gonna hate what you're doing. Yeah, that's no good.
Balance is always good.
Yeah.
Yeah. And what was it about physics in particular that drew you, like made you decide between chemistry and physics? Was there anything that was different?
Just learning about how the universe works, really. It's just these, those questions, the curiosity of how do things really work down at the microscopic level. Yeah, that's, I think, what really interested me is just developing like a deep understanding of how the universe works, really. And yeah, and physics kind of helps to sort of answer those questions, and then you do a whole degree and you're still like, this we still don't really know that much. But,
yeah. I'm incredibly biased, but I agree.
Yeah.
Oh, that's great.
Anything else might be good to talk about?
What do you think?
I have no thoughts.
No, I think that was great. I don't know. Was it
Like,
did you find it hard to transition to industry? Like, did you?
Yeah, I applied to the company. I mean, I sent out a few applications. I applied to this company, and I had actually visited this company before as part of the lab and gave a talk there. So that probably helped. It can be pretty challenging to get these positions now. I know that, I don't know, the job market fluctuates, but yeah, I think it's been pretty challenging lately. Another thing I could talk about is, well, I could also talk about this like hobby project that I did a while ago, which was making a scanning tunneling microscope. So this was like purely for fun, something that I think probably helped also. Definitely gained a lot of skills from doing this. It's just building a a scanning tunneling microscope, which is a microscope that scans a needle across a sample, an electrically conductive sample, to build up an image with atomic resolution. So you can take pictures of atoms, basically. And yeah, so I wanted, these are used in research quite a bit, and especially in physics research. And it's something I learned about in CEGEP, which is a thing we have in Quebec between high school and university, which is also very helpful, I think. And yeah, I just wanted to see how, if I really build one on a budget, would it actually work? Like, how well can it work? And it turned out it worked really well. I was getting atomic images. And I learned a ton about, especially electrical engineering, doing that, and some mechanical stuff like precision machine design, which was also very applicable to the lab work that I was doing, which also involved controlling nanopositioners and just positioning optical elements to like nanometer scale accuracy. And yeah, so
How expensive did it end up being?
the first iteration was probably, I think it was like a few $100. I never really fully costed it out. But yeah, it was like made. I kind of just like took the body was like a slab of aluminum, just cut in half, and then with some holes drilled in it to put like precision adjustment screws in, mount a nano positioning scanner on, which is really just a modified piezo speaker element. So very cheap. This was invented by someone named John Alexander back in the 90s, and so I wasn't sure how well it would really work, but it worked actually spectacularly well. Yeah, so that, and then it was just the microscope itself is fairly simple, and then there's a bunch of electronics that go with it. So I learned a lot about how to design like mixed signal electronic circuits where you have a lot of precision analog signals. So you have to measure this. You actually have quantum tunneling happening between your needle and your sample to like pico or nanoamp level currents flowing. And you have to design sensitive amplifiers to measure that. And then, you know how to use analog to digital converters and just build circuits up from chips, and design circuit boards so that you can, just control the scanning and everything. And so what the microscope does is it runs this current by applying a voltage between the tip and sample. And they have to be separated by a few angstroms. So fraction of a nanometer without touching. If they touch, your needle has to be very sharp to get good image quality, good resolution. And if they touch, then you kind of ruin that. You'll blunt your needle. So you have to run a feedback loop that measures the current between the two and maintains it, or tries to keep it constant by adjusting the height of your scanner. And the scanner is extremely precise. If you design your electronics well and you design your microscope well, then yeah, you can absolutely position it with sub-nanometer, sub-angstrom precision. So you run this feedback loop while scanning, and when it comes to kind of hills and valleys, it will track them to keep a constant current. And by keeping a constant current, it keeps a constant gap between the two, the tip and the sample. And then it builds up this kind of like 3D topographic map of the surface that you're scanning, down to the point where you can see the individual atoms sometimes.
That's really cool.
Yeah. And then like it had to be isolated from vibrations, so it's on a big like heavy steel plate hanging from springs. Yeah.
And this is in your garage, or?
This is like in my like next to my desk. Yeah.
That's awesome.
Yeah.
What do you use it for?
It was just for fun.
Did you image anything cool?
I have pictures of graphite atoms. I have some cool pictures of a gold surface that looks like a mirror. But then, at the nanoscale, of course, it's got hills and valleys, and you can see atomic level terraces. So like, it looks like it has this kind of layered structure where all the layers are one atom thick. So that's pretty neat. I don't know. The pictures just look cool. There's just,
That was really cool.
yeah, no purpose beyond that. Actually, I think it would be it has potential as like an educational tool, like something for physics or chemistry education. I learned about this in a chemistry class, and I didn't actually, I've never actually used one other than the one I built myself. Though I've used atomic force microscopes, which are very, very similar. It's built on the same technology, basically. But I didn't start using them until I was in grad school, really. Um, and I think, yeah, like if I had had the opportunity to use something like this in high school or maybe in undergrad, um, that would be pretty cool. Like to actually take my own image of atoms and see what's really involved in doing that. I can send you
That'll
pictures.
be
Yeah.
great. We'll credit you. Citation, Dan.
You can go to
Dan machine.
dberard.com.
Ah,
It's
there you go.
Dberard. It's my name, and you'll see pictures there. But like, here's a picture of some graphite atoms. Oops. Yeah, I mean they look like blobs.
Oh, wow.
But you can see they're in a pattern. And so this is the crystal structure of graphite, which is made up of layered 2D sheets called graphene, and they're just stacked on top of each other. Yeah, and then the microscope looks, let's see, I mean, the whole setup looks kind of like this. I don't know how they can see that on the camera, probably not very well, but yeah, I mean, there's a big plate here hanging from springs, and then there's this tiny little microscope. It fits in the palm of your hand. That's sitting on top. Yeah, and there's some electronics at the bottom. And that's it. So, yeah.
Yeah,
Here's
usually
a
those
picture of
machines are pretty
gold.
big.
Oops. Yeah, here's a picture of a gold surface where you can see the atomic level terraces, and you can see kind of these boundaries. These are the grain boundaries between the sort of crystals that make up the material. So this one sheet of metal is made up of many sort of 100-ish nanometer sized crystals. Yeah, and you can see the boundaries between all of those. It's pretty neat.
Really cool.
Yeah. It was a fun one.
What's your next image?
The problem is you can't look at a whole lot of things without ultra high vacuum. Because the gap between the tip and sample has to be so small, sub-nanometer, and they both have to be electrically conductive, that actually limits you massively, because most conductive materials are metals, and most metals react with oxygen in the air very quickly, and they'll form what's called a passivation layer on the surface, which is just a layer of metal oxide. So something like aluminum, even though it's very conductive, it will form, several nanometers of oxide on the surface, immediately when it's exposed to air with a very small fraction of a second. So you can't just clean it off and image it, because it just immediately forms again. So you can't look at aluminum on this microscope because the tip will just jam into the oxide layer, and that's it. Like, it's not going to work. Gold does not oxidize in air. Neither does platinum. Copper does, but it's slow. So you can look at copper if you clean it. Same with silver, it tarnishes, but if the surface is clean, then you can look at it for some period of time. Graphite works too, it doesn't oxidize. And there are some kind of weird semiconductor materials that work too. I've looked at molybdenum disulfide, which is very sort of similar to graphite in a way. It's kind of this like flaky sort of material that forms these like 2D layers. For almost anything else, you need ultra high vacuum. So if you remove almost all of the air, then you can bake off the oxide layer on materials. If you want to look at a metal or like silicon or something like that. So, silicon has like you might want to look at often because it's, a semiconductor. It's extremely important. So if you just heat your sample up enough, you can sublimate off the oxide so it vaporizes, and then you just have your pure surface left. And in ultra high vacuum, there's not, it will take quite a long time for the surface to re-oxidize, but it really needs to be ultra high vacuum. If it's just high vacuum, it will reoxidize in maybe a few seconds. Yeah, and you want to take that down to like minutes or hours. So,
And doing
yeah,
that would
and
make it
that's-
no longer accessible.
that's not, yeah, I'm not doing that because that's just like absurdly expensive.
That's
Yeah.
fair. Well, the gold looked really cool, as did the graphites. Oh, that's awesome.
Yeah.
Well, we'll put your pictures from your website on.
Perfect. All right, thanks.
Oh, thank you so
Yeah,
much.
it's fun talking.
You have any other questions?
Yeah, I think you're good.
Okay.
All right, great.
No.